Hello, future scientists. I'm Adam. Join me in this adventure where we will review how to solve energy pie chart problems in physics. Energy pie charts help us visually understand how the law of conservation of energy works by looking at a system in 3 stages: start of the process, during the process, and end of the process. Here you can see all the symbols I have used in the pie charts: kinetic energy, gravitational potential energy, thermal energy, elastic potential energy, chemical potential energy, and electrical potential energy. Here is problem number 1. Isaac, of mass 60 kilograms, bikes at the bottom of a ramp at 5 meters per second. He bikes up the ramp and arrives at the top where he bikes at 1 meter per second. First, we have to identify the system. The system here is the biker and the ramp. Now, we are going to draw the energy pie charts for the 3 stages. And I'm going to call the 3 stages A, B, and C. Keep in mind that we are going to include friction. This diagram shows the 3 stages of the process. Always it's good to have a diagram in front of you when you solve an energy pie chart problem. It does not have to be fancy. It can be as simple as a free body diagram. Here is the pie chart for stage A. So at stage A, the biker has a high velocity, which means he has kinetic energy. And since there is friction, there is also thermal energy. EK is energy kinetic and ET is energy thermal. In stage B, some of the biker's kinetic energy has been converted to thermal energy, and some of the kinetic energy has been converted to gravitational potential energy since he is climbing the hill. So the EK has gone down, ET and EG are growing. Here is a pie chart for stage C. The biker has much less velocity than before, so his kinetic energy is much less. His thermal energy has also grown because he's been biking for a while, and he's at the top of the ramp, so that means his gravitational potential energy has also increased. Now we are going to answer some questions based on the pie charts we just drew. So the question is, if the thermal energy at the bottom of the ramp, which is at stage A, is 0 joules, what is the total energy at the bottom of the ramp? So at the bottom of the ramp, the biker has EK and ET. But ET is supposed to be 0 joules, which means all of the energy at stage A is kinetic energy. Kinetic energy is 1/2 mv squared. Plugging in the values for mass and velocity, we get the kinetic energy as 750 joules. So that is the initial energy. Now we have to figure out the kinetic energy at the top of the ramp. Again, we are just going to use the formula. Kinetic energy is 1/2 mv squared. Mass is still the same, but the velocity is different. You plug in the values in the formula, and you get the kinetic energy at the top as 30 joules. Next question. What is the potential energy at the top of the ramp if the thermal energy at the top is 200 joules? So if you look at the pie chart, at the top of the ramp, the biker has thermal energy, gravitational potential energy, and kinetic energy. And the thermal energy is given to you as 200 joules. The kinetic energy we just calculated at the top as 30 joules. Now we know that the entire energy that is at the stage A, which is the initial stage of the process, was 750 joules. So what we're going to do is take away 230 joules from the 750 joules, and that is equal to 520 joules. So this 520 joules will be the gravitational potential energy at the top of the ramp. Now we have to figure out the height of the ramp. So the height of the ramp can be figured out by looking at the GPE at the top of the ramp. The gravitational potential energy at the top of the ramp is 520 joules. And EG equals weight times height. The weight of the biker is 600 newtons. So height will be equal to 0.87 meters. Now let's go to problem 2. An electric car travels as shown in the diagram below. Draw the energy pie charts for the 3 stages. Include friction. Here is a diagram showing the 3 stages of the process. Here, the system is the car and the road. One thing that you have to pay attention to is the length of the velocity vector. Here, the velocity vectors are the same for stages A, B, and C. So that means the car is traveling at a constant velocity. Because it's an electric car, the potential energy of the car is electric potential energy. So in stage A, the car has a lot of electric potential energy, shown as EEC. It has a small amount of thermal energy, and it has a certain amount of kinetic energy. In stage B, the car has the exact same kinetic energy because it's going at a constant velocity, lower electric potential energy because it's been running for a while, and higher thermal energy. In stage C, the car still has exact same kinetic energy, but the electric potential energy is even lower and the thermal energy is much higher. Now we go to problem 3. A wind-up toy train moves on the floor as shown in the diagram below. Draw the energy pie charts for the 3 stages. Include friction. And here you can see the 3 stages of the process. The system here is the toy and the floor. As you can see, the initial velocity is very high. The velocity at stage B is a little bit lower, and the velocity at C is 0 meter per second. And here is the pie chart for stage A. Because this is a wind-up toy train, the potential energy is elastic potential energy. So at the start, it has a large elastic potential energy, which is EEL. It also has a large kinetic energy because it's moving the fastest at this point, and it has some amount of thermal energy. And here is the pie chart for stage B. So now the toy has a smaller kinetic energy because the velocity is smaller elastic potential energy because it's been running for a while, and higher thermal energy. Here is the pie chart for stage C. The toy has no kinetic energy because the velocity is 0, no elastic potential energy because the toy has come to a stop, which means all of the energy now is in the form of thermal energy. Hope these energy pie charts helped you to understand the law of conservation of energy visually. Happy learning. Thank you.